My name is George Kierstein, and I'm a government contractor for Global Science and Technologies that works for the National Centers for Environmental Information, all like lots of acronyms. But that is the former National Climatic Data Center and the foremost location for pretty much most of the world's climate data. And I'm going to start off warning you that there's not an outline, because that would be misleading, as if I had some linear progression, because I'm going to be making gross, broad generalizations that are likely to piss people off, or at least be controversial. Instead, it's kind of going to be more like this. I'm going to start at a very high abstract level with a completely seemingly unrelated topic, kind of drill down through data visualization and contrast it with what we call big data now, which is typically industry, and to sort of then contrast it with the science and its visualization problems. And then we're going to look at climate data, and then we're going to demo the work that my co-worker here, Egg Davis, and I have done to visualize multivariate climate data with very different types of data sets. So, we all know this. In fact, that was my best attempt, and that's supposed to be a dove. Sad, but obviously there are some images and some ways of visually communicating that are so profound that they really do change people's minds and hopefully their behavior. We'll see about that last one, though, in the long run, with respect to climate change. So I'm going to go through what brains have to do with it, in part because back after the first tech bubble popped, I did what most people did, which was go back to grad school. And I did that in computational neuroscience, which has a lot of brains in it. So and the point I'm really trying to make here is that our neural architecture has left us with some subtle cognitive biases, and let's be honest, there are some not so subtle cognitive biases as well that are in play here. So it's arguable that at least half of our brain is devoted to or involved in visual processing. That's not going to go through any parts, but that kind of gives you a gestalt overview of what people think the visual parts of your brain are, which is quite a lot. Now, basically, although we have this seamless perception of the world, or at least seemingly so, we in fact completely manufacture it all the time. It's a complete lie. We have this is a isodensity map of the retinal ganglion cells in our eye, and this shows you the shape of kind of how our retina is laid out, which is circularly symmetric, and it kind of falls off pretty rapidly. Actually, inside your brain, it's logarithmic, and pretty much all of your vision comes from that tiny point in the center, which of course is why we have to look all over the place. And this is what it looks like if you do a reconstruction of what your very first part of your brain, sort of after it's represented in cortex. You can see that the only real definition is inner eye, and it falls off pretty rapidly from there. But that's just the beginning of the level of complexity that goes on when your brain tries to give you this seamless perception of the world, because that there is the retina with a lot of blood vessels all over the place, and they're obstructing the actual retinal ganglion cells. So that nice map is not actually a nice map because it's covered with veins that block certain cells. And it's not like you sort of have a static eye. What this is a picture of something called microsaccades. Unconsciously to you, when you look at anything and you take it in, your eye, in the time course of 20 milliseconds or less, actually traces a pattern like this to pick up details so that you can translate it into a seamless view of a larger scene than your eye could ever take in at once. And it just keeps getting more complicated from there. This is a picture of the dorsal and ventral streams of where kind of visual processing starts to carve out and bifurcate. So it really has left us, though, with an impressive array of tools that we kind of unconsciously leverage all the time. And that is really handy because we use it primarily in the sense of data visualization. You know, we have comprehension of the world and we want to visualize it. And we've always been curious and tried to formalize it. Some of these are from art, some of these are from, you know, architecture. It's arguable whether or not the actual thing we're looking at here is revealing a fundamental principle of nature or just the types of patterns that are very well attuned to our neural architecture for vision. For example, that picture on the bottom right with the golden spiral ratio is perfectly sort of suited to our particular kind of like fall off, because the real center of action is the one right where there's the cluster and you're looking at it, but at the same time you still get the sense of motion all in one gestalt view right immediately, because you don't really have to look at it all to notice that the far sort of left is got something going on, but the real center is where you're really interested. So there's lots of things like that in the brain, and it's pretty interesting that we ostensibly have these huge cognitive biases. So, and we've always tried to leverage them. This is an awesome map, perhaps one of the most famous, best visualizations ever. And it is a map of Napoleon's invasion of Russia in 1812 by Jacques Minard. And it's beautiful and expressive and looks really modern in a lot of senses. So, post the Industrial Revolution, we pretty much have only gotten more and more data, and it pretty much looks like that's just going to be the way it is. And we need tools to interpret this complexity. So, luckily for us, computers came along, and they were very popular. But unfortunately, like the PowerPoint slide here that I think I got off of some random 10 worst PowerPoint slide sort of website, it is really not very helpful. And in this era, that sort of idea that was coupled with accessibility of these tools kind of led to a confusion around what even good visualizations should look like and how people should really use them. I assume this was an improvement of some kind, perhaps not a very well executed one though. And of course, I couldn't help myself. This, of course, is Edward Tufte. And along with many others in the 50s and 60s, he really started to see the possibility that the modern computing, you know, and all of these other sort of tools that give us way more power and expressiveness than we've ever had before could be formalized using a lot of techniques. And I'm just going to say I'm a huge fan. Now, this is the first time I really encountered this idea of quantitative information and data visualization, and it left a huge impact. It really did leave a huge impact for a lot of people, and he laid out pretty much many of the fundamental principles that we ultimately use today. And I'm not going to get too technical or too nitpicky because I'm sure that I will make massive mistakes because it's an enormous discipline now and lots of subfields. Like this, you know, here we have a nicely thought out diagram that demonstrates some of the downsides and upsides of how to do things, how to do layout. And these come from places of, cognitive neuroscience influences like attention studies and so forth. And we're starting to make some significant progress in how to formalize really understanding the most effective ways to visually communicate with the tools we have. Like that. And we could go on all day, and I would love to show lots of sexy data viz, but we don't have time. So I'm going to move on to big data, or mining analytics for fun and profit, which really kind of makes sense. I'm going to try to do my best movie voice. In a world run by computers. Oh, all right. Well, it makes sense that we would really need to start to leverage these because we have more data, and that any one human could just sort of look at. In fact, it's become a global effort to even understand the volumes of data we're producing, and eventually, if not already, the volumes of data that computers are producing for each other. And our expectations now of true, like, instantaneous communication and so forth have kind of left us no choice but to become really good at this particular style of communication. And in my opinion, it's probably the best chance we have to really tackle some of these hard problems like climate change. So this is probably the most contentious and hilarious sort of part of the talk, because I'm going to make broad generalizations which are potentially inaccurate and or a little bit like, controversial. We can debate about it outside. So on the developer end of the world for data visualization, and I'm pointing this out as a contrast to the situation that climate data visualization is going to have, we can see that in some sense, we've had this nice path starting from the 50s and 60s with network computers, where computer scientists have generated data, but in a pretty systematic way. And it's kind of interesting to point out that ARPANET was in 1969. Now, as a point of contrast, the invention of the telegraph, 1835. Arguably, the first sort of, weather measurement and prediction that would be considered modern was 1861. And by 1901, nation states had begun to actually systematically try to put this, into archives and keep records of it. And it worked, at least on paper. So developers also love interoperability. Whether or not we achieve it, that's always a contentious point, but at least we try. Way more than I think scientists do when they handle their data. And the tools we don't want to rewrite the wheel every time we encounter something. And I think developers as a community really do want to share. Like, there's just no value in kind of hoarding your little nugget of gold when all of us could make use from it. So, and there's plenty of other things that could be thrown in here, but I think that kind of covers the point. And we all know it's not entirely accurate. It's certainly not that easy. Now, what about data viz in science? I argue it's dragons all the way down. Why? Because of physics. For instance, you start off with instrumentation. They're often incredibly complex. There's a tiny guy down there just for scale. That's the Large Hadron Collider. They often measure aspects of a phenomena, not even the phenomena directly itself, which lead to even more complicated instrumentation to validate something or not. They also have to be calibrated because they're sensitive and very, very, expensive and complicated machines. These are diagrams of two satellites. They're platforms for Earth science observation, and they have their own problems with calibration, because you can't just go, hey, some sensor seems to be weird. Why don't you pop out there and figure out what's going on, or at least not very easily. And in this case, the calibration aspect for temperature is this weird black body box. It's as dark as can be humanly possibly made. And it aims its sensor into that to calibrate how off it is. And they fluctuate all the time, even if they're not gone or down, because there's all kinds of particles and things that throw off their ability to do their job in space. Not to mention, these data sets are really difficult to merge because they're so different from each other. They have an entirely different sort of perspective, history, and so forth, which makes it an open challenge still for how to do a systematically effective job in making sure that you can tie them in together. And scientists, this is very diplomatic, but they tend to be insular, and they stick with what they know. And more. And so, oops, lost track. Oh, so consequently, this is a pretty common visualization. This is modern. In a way, it's really precise because it demonstrates sort of the time course dynamics of training up a neural network. And, it doesn't look too bad, but unless you really understand what you're looking at, the methodology, the neural network architecture, and all the rest of it, it is really difficult to parse what their point really is. On the other hand, this is a gorgeous image. Made the cover of Nature Neuroscience in 2000 and is still basically one of the most famous neuroscience images ever made. And I'm almost tempted not to tell you what it is because you have this intrinsic feeling because of its elegance and symmetry to kind of not care. But I will anyway. So your brain is basically a millimeter thick, kind of gelatinous sheet about a meter wide, meter on a side that's kind of squished and crumpled up into your head. So when you see the picture, the early picture with all those folds, that's because it's just basically the crumple of your brain fitting into your skull. Now, in the very early stages of vision, which is what I focused on in my work, there are these little cells that are tuned to respond to stimuli at certain angles. That's all they're just angle receptors, basically, and they get all excited when they see an angle. But since you're on a sheet, you kind of have a weird tiling problem, right? If you're going to have lots of them, how do you do the loop? When you get back to this loop, where do you put it in order to actually lay it down on a map? And it's not really entirely clear exactly how your brain decided to do this. On the right is like that's the millimeter of your little chunk of cortex. And they've plotted out these nice left-right columns, but the receptors live in these nice vertical orientation columns. And you can kind of see the orientation on the side of the right. And on the left, you see how they figured out, how they took that picture, which is kind of creepy. But it really involves a lens and a camera and some light. The problem with that image is kind of profound. So my advisor, Eric Schwartz, he came from a high particle physics background and was very concerned about the lack of rigor in most of neuroscience's research because of the biology-driven kind of history of where cognitive neuroscience came from. So he wanted to make sure and knew that you could introduce weird symmetries by blurring things, that this wasn't in fact a systemic error that basically made that research not say anything useful because it could just be a systematic bias. On the left is a Monte Carlo simulation they did of the optical imaging system, and on the right they just sort of wanted to make sure that their their Monte Carlo model produced the same kinds of results from the original paper, and it looks like a pretty good fit. And this is a animation from John Polomeni, my co-lab partner, who demonstrated that as you adjust the lens, he's kind of running through the focus depth of the lens, you can see that the little pinwheels and the symmetry all just move around. Like there is no stability within that system with that particular recording device. And it's really remarkable that today, even to this day, I found a paper that is kind of still interested in these orientation columns that didn't even acknowledge that this systematic bias could even exist. They just sort of blithely assumed that the original paper looked so great that they should just go with that and continue to do research, which is a real problem in science because over time, these time scales of adoption of real results just don't percolate out due to the kind of ivory tower effect. And that is in real contrast to how we tend to publicize and want to get on top of real problems that are producing systematic bias and causing all of our stuff to go off the rails. And in short, the worst part is that scientists are rarely developers. I've seen some incredible code. In fact, in the building, a coworker of mine has removed, I think, 345 go-tos to date from this one piece of code that was written 25 years ago, I think, started by one person who has then passed it off more than once. And in fact, I worked on a project not too long ago with a scientist who was interested. He's retiring, but he had never even heard of the concept of version control. He was into it once I explained what its use was, but he's like, that sounds like a great idea, that's pretty typical. And how about climate data then? To me, in a real sense, it's only really become relevant to us until like very, very recently, and that's had some real side effects. This is a quote from one of my favorite thinkers of planetary change, Frank Herbert. And I think that's really quite true and pithy at the same time. So climate data, I feel, is unique in some really interesting and important ways, which is these are the longest continuous data sets humanity have ever collected. They go back at this point somewhere, the oldest ones are at least 150 years old. And they have a distinction perhaps a little bit different from, not business analytics and business big data, where the provenance is scrupulously monitored and it's a very intrinsic part of their process. Not only because if you have data going back 150 years, it's not like you can walk down the building and ask someone why they made a choice and it didn't work out too well, because they're dead. And of course, it's a global effort, and in a way that is really truly a global effort. Pretty much every nation state that has the money or the capability has satellites in orbit doing this work, and they're all happy to shove it at NCDC, or NCEI, pardon me. We just changed, so it's still having cognitive dissonance about that. But it really is this global effort. We get data in from Indian satellites, Chinese satellites, and everybody's happy to be a community on this particular sort of topic of how we do a good job, which satellites go where, so we have global coverage. It's a real cooperative kind of thing because basically it needs to be as the scale of the problem. And these generational scale impacts are something kind of new, I think, to how people even perceive data, because basically the brain part of the talk is your vision is far from the only place where you have these blind spots that are due to your cognitive, architecture, shall we say, like so. And that's a real problem, but I'm going to segue a bit into a bit of history of the building because I think it's pretty interesting. This is on the top where all of the data, climate data for the world used to be stored. It's a lovely old building in Asheville, North Carolina, that had an incredible amount of paper data, punch card data, microfiche data, and it was started basically in, my notes say, just because I want to be specific, this started out in New Orleans in 1934. It was transferred to Asheville in 51. So by then, there was millions of paper records and so forth. And in 1993, of course, they moved out of the building, which is a shame because, man, it's beautiful inside, I gotta say. But at this point, the NOAA and the NCEI institution archives basically 99% of all NOAA data. And I love these statistics. They've got 320 million paper records, 2.5 million microfiche records, and then petabytes and petabytes of data. So let's see. And there's all the same issues that you struggle with in science itself. Like, for instance, this is a picture of one of the instruments that our data set, generated data from, and it had a weird problem. In fact, Egg was part of this story, although it's a great anecdote. At one point, the CRN people, who is the Climate Reference Network that's actually responsible for these instruments, they found some weird glitch in precip data in one station in Florida. So lead scientist, being an instrumentation specialist, doubled down on trying to figure out what went wrong with the instrument. And many other attempts were tried and try to think through failure modes and so forth. And it certainly was not just a sensor failure because there's 3 weight sensors on there and they're all in agreement. So they sent somebody down there, and when they did, they discovered that tree frogs had decided that that bucket was the best place for them to live. And of course, they'd hop in and out of it occasionally, introducing weird biases into the data that would otherwise be really difficult to debug from afar. And not to mention, along with the generational timescale of these types of data sets, which really are our first attempt at understanding how to pass data down through the generations in a way that it makes sense and is sustainable and useful, those generational effects have caused all kinds of problems that we see commonly but don't really hurt quite as bad, like someone decides to change the header in your data. Imagine that happening over lifetimes, and we typically only keep jobs a few years, so forth and so on. That's a little less true within the scientific community, but it still happens pretty frequently. The not built here syndrome, come in, you look at the insanity that you got left and you're just eager to fix it. But you're passing that on to someone else, and they're passing it on to someone else ad infinitum, and it's already been happening for, at least 70 years at this point, and it's not pretty. Not to mention that the data changes, These instruments become more sophisticated every year. You put a new satellite up there, they've improved the sensors, they've added a whole bunch of other kinds of sensors, and so you can't always easily compare the data that was 50 years ago, missing most of what the new data has. And again, these data sets, many of them are manufactured from code, and they have their own idiosyncratic choices about what to do. And sometimes even the same nominal concept like temperature is thought through in a completely different way between two different data sets. So you almost have no easy way to figure out how to merge them. Some of that is due to just the physicality of the measurement device. A lot of satellites have a 5-kilometer little pixel, and then the new ones have a 1-kilometer little pixel, and you want to merge those two to try to understand something specific. How? It's not clear. And I want to be a little fair, because I'm painting a pretty picture of how sort of really difficult and frustrating it can be to actually work on these data sets, but it's not like they don't know. And it is constant sorts of problems that they really know they have to actually address. But, we don't live in the type of country that fully supports this notion and backs it with the kind of funding and respect that I think it deserves. And that means that this is a pretty typical visualization of climate data. Now, it's not bad in a sense, but you can't really tell what the error bars are. And worse, it's one-dimensional, and it's probably just one section of one data set. And there are hundreds of these data sets that all have facets of the climate problem that are looking at it in different angles. And that is not great when you're trying to express this to someone who is not a climatologist. I'm not a climatologist. I barely understand a lot of the data sets that I work on, and that's not helpful when you want to make sure that everyone else in the world can work on this problem too. It's just so multidimensional that Egg and I thought, how hard could it be to do a better job of merging two very different data sets? Well, or in the best owl voice, 3. So this is our data. We have two wildly different data sets, one of which with completely different instrumentation underneath them. The one on the left is from the Climate Reference Network, which is, trying to address, is a really great data set because they are the first one to, from the ground up, choose to try to make this a beautifully designed, pristine 50-year period data set. Their goal is to make this clean and continuous and well thought through so that 50 years from now, you will not have any of these fractured problems. And, hopefully it'll continue, but that is their goal, and that's a laudable one, but it's sad that that's the first time that, that's become a conscious thing to try to do. Now, their ground stations, so the little dots you see are where they're located geographically. And the region here we're looking at is the region of data that the visualization is going to be confined to. So on the right, we've got this thing called SWIDI, hail. We're going to look at hail data because hail data is one of the most damaging and important types of data, types of weather effects to understand. And it's typically still derived from radar data, which goes back a long time. I think radar was built in 1939. And it is still the main workhorse of how we detect a lot of weather patterns regionally. That is a mesocyclone, and this SWIDI actually stands for the Severe Weather Data Inventory. One thing that I think most people don't understand, because it's difficult to communicate this, is that most of the data sets that people encounter when they think of climate data are actually generated out of an algorithm that someone wrote. There's raw weather radar data underneath there, and that kind of gives you sort of the raw picture. But then after an algorithm is run, it does things to try to detect hail by looking at reflections in the clouds in a mesocyclone type of weather pattern. And ironically, it's so detailed that they just decided that they'd take a quarter and then they decide to sort of say, oh, well, of course, hail's circular. So when they give you a measurement size for how big it might be, they're saying yeah, it's about a quarter, size of a quarter, because there isn't great language yet to also describe the types of real complexity of these weather phenomena themselves still. And basically then our approach started off with a hand-rolled framework, which was quickly abandoned for Luminous. It provided a lot of extra affordances that we really wanted to avoid having to hand-roll ourselves, and it really removed a lot of the unnecessary complexity for us trying to get a data viz going. And we picked React because React is awesome, and I can't imagine that people don't want to use it, but we went with Reagent at first, and I've been quite happy with it, but after this morning's talk, I think Next is definitely going to get checked out for a lot of great reasons. And we used this awesome JavaScript library called MathBox, and it's amazingly well written. We're actually on the first version. It came out another one and just blows away the first version. Decided to work with that, and it's basically a library that targets WebGL, so it's running super efficiently on your GPU with 3GS and tQuery. If you have more questions about that, Egg's going to have to answer them. But it gave us a really nice way to have a good visualization tool that mapped into the three-dimensional multivariate kind of space that we were looking at that's closely, sort of fitted to the type of data that we're going to be using. So here is just MathBox running random data. So it's really nice, and you can move it around if it'll let me. Oh, there we go. And it has other affordances, but you kind of get the point. I'm going to show you a little bit of the wrapper that we needed to use in order to be able to get this to, well, hold on, let me go back, because there was a couple of extra points, and unfortunately they're on my, wait a second. Anyway, there were a lot of challenges trying to integrate a really stateful library into a nice sort of stateless, framework and concept. So Egg here wrote this part of code, which is an attempt to write a wrapper to make it more stateful. And there was another pain point here where once that happened, we still had to, avoid a lot of problems that are combining Reagent with this as well, where it's got, an impedance mismatch because it's watching for certain things, R-atoms, and we had to create an adapter layer to be able to keep these things all playing nice and to make sure that the MathBox internals and the Reagent sort of internals did not really have to know about each other to kind of keep it nicely separated. And it's nicely sort of condensed and expressive, so you don't see a lot of the problems. We chose to keep an instance around, and basically it's pretty nicely updated with the Reagent atom underneath it. So here is CRN data. Basically, these are 6 stations in that region that I showed you on the map earlier. They're lat-long, organized, so it allows you to see some diurnal patterns. This is about a week's worth of data of temperature for each station. And you can kind of tell, here's the day, as the week rolls on, if we let it play long enough, you'll actually see seasons. You can clearly see the sort of seasons segueing and so forth. And basically, since we are aiming to represent more than one data set, we really needed to leverage something like this in order to kind of do, go. Okay, fine, I'll use my mouse. In order to merge them. So this is hail data being visualized with the CRN data. So the SWITI data set basically is a bunch of severe weather events. They keep track of what happened. It's a little bit misleading in detail because there's probabilities associated with it because it's a calculated algorithm. So they're basically saying, with a certain probability, we are pretty sure that hail fell right here at this time. And that's about all they can do, of course. So what you'll also notice is really interesting, I think, when you have multivariate kind of data like this, is that you can start to see, suggestive regional patterns. There's one isolated storm here, that's pretty far away from these other two. And then you get these clusters over time. And of course, you will watch, although when I'm not playing it that long, because looking at just the other things done. Yes?
Sorry, what are the axes? Is that like physical space, like geographically?
Yeah. This is lat long division. It's not to some particular scale at this point, though. And the hail blobs don't indicate sort of what exactly the probability of these events were. We just went with, somebody said that it was very likely that, it was likely at all that hail happened at this time. But it does give you a way to sort of check for, it gives you more information about either one of these, because you could plot the hail thing, you could plot all the hail data alone, and you could plot the, CRN temperatures alone, but it doesn't give you a lot of ability to say, visually and kind of have an intuition that, this particular type of storm in this particular area or this particular weather pattern was quite regional or this one was quite broad. And it is I think, a better type of approach in general. And we didn't get done with all of the polish that we would like to, but I think it does, lend itself to having a slightly better understanding of how these two types of data sets that are both very highly provenanced and mean certain things to certain people, might be able to be merged without, dealing with the nitty-gritty of the fact that they never were intended to play nice together. So
that's in the browser too.
Yeah,
that was a lot of the work that we did. I mean, of course, people have been doing complex 3D visualizations for a long time, but it's only fairly recently that that's become plausible in the browser.
Right, what he said. Yeah, so thank you, and if there are any questions. Anybody, questions?